Welcome everybody to the first video of further topics in probability. This is the first video of the unit, but not the first video I'm recording in this unit. I started recording last year in 2020 when the pandemic took off in the UK, and I started recording at the middle of the material. So now I'm going to do it from the beginning until that point, which has already been recorded. So this is the first video of this unit, therefore. And in this one I'm going to review some of the elementary discrete integer value distributions which we are going to use later on. It's mostly just a review of probability 1 and just introductory probability. Discrete random variables, denoted by x, are those which can take only on countably many possible values. And so if it's countably many, then I'm going to denote these possible values by little x1, little x2, little x3, and so on. Since it's countable, you can actually list these values. So there is just a list of all the possible values. So these are the possible values. And just a small remark here that random variables will often be denoted or shortened by RV. So from now on, if I say RV or write RV, that's random variable. Okay, so these are the possible values, and so what you want to deal with here is the probabilities of these values. So the probability mass function sometimes also abbreviated as PMF. So I'm going to add that here, PMF, probability mass function, is just the probability of these particular values taken by x. So P of xi is just going to be the probability that xi happens to be, x happens to be that particular xi. These are probabilities, so obviously they are non-negative. And of course, if you look into all possibilities for the xi's, then since these events here are disjoint and they span the whole sample space, the sum of the probability of xi's is 1. We are going to have a little bit of comments on this later on, but for now let's just keep it at 1. So the mass function is a non-negative function on countable many possible values that sums up to 1. Now in this unit we are almost always going to deal with integer valued random variables, and so that means that instead of x1, x2, x3 and so on, I'm just going to denote xi by I, and I will mostly be non-negative integer, but in general I could be any integer number in Z, including negatives. Okay, and then this sum of the probabilities equals 1 will transform into sum of the pi equals 1. So for integer valued random variables, the possibilities are integers, and the mass function values on those integers sum up to 1. So that's what a random variable is. Now, so I'm going to concentrate on these from now on. If you want to take an expectation of this, and this should be familiar to everybody at this level, expectation, sometimes we're going to say mean of these random variables, is going to be the sum of I times pi if this sum exists. And straight away I'm going to explain to you that there are essentially 3 cases. So case 1 is that E of x exists and is finite, actually 4 cases. Case 2 is that E of x exists but infinite, positive infinite. Okay, how could that happen? Well, if you look at this sum here, this sum in general, if I can go to negative, will have negative parts and positive parts. If the positive part of this sum, so when I is positive, is infinite, and the negative part of this sum when I is negative is finite, in that case the total expectation will exist and it is going to be infinite itself. Another case, of course, is when the expectation exists but is negative infinite. That's another possibility. So if the negative part of this sum, when I goes negative, is infinite, but when I goes positive is finite, then the total sum will exist and it is going to be equal to negative infinity. And finally, it could be the case that e of x does not exist. Doesn't exist. That's another possibility. So these are 4 possible cases for the expectation. Okay? And so what is this case when the expectation doesn't exist? Well, that's the case when both the positive part of this sum, when I is positive, and the negative part of this sum, when I is negative, is infinite. And in that case, there is no way to do the total sum. It doesn't make sense. And in that case, we say that Ex doesn't exist. Mostly, I suppose you've seen random variables with finite means, so when E of x exists and is finite, but occasionally we'll encounter random variables with either infinite means or sometimes random variables with no means at all. Okay? So that's the expectation of random variable. And then let me briefly tell you about the variance. So suppose that you have a random variable. Well, let me tell you about moments first. Moments of a random variable is expectation of x to the n. I'm assuming here that n is a positive integer, and this is of course just defined as the sum of I to the n times the mass function. If exists, again, when n is odd, then we might have some problems with existence. And in general, if you look at a function of x, then the expectation of that function is going to be the sum of that function times the mass function. And so once you have the moments, then of course you can define the variance of x, actually in 2 different ways. You could say it's the expectation of x squared minus the square of the expectation. And again, a notational remark here. If I just write e of x squared, by this I mean the expectation of x squared and not the square of the expectation. And then everybody knows that the variance has this equivalent form of expectation of x minus mean squared. This way, again, the square is underneath, this square is underneath that expectation here. Okay, so this is just a very brief review of the generic notions for integer-valued random variables. Usually we only talk about variances when we have a finite second moment. If the second moment is infinite, then this variance is infinite. The variance is never negative, as you can see it from here. If you don't have already a first moment, then you just don't talk about variances. Okay, so what's coming next is I'm going to tell you about specific distributions. So examples or particular types of random variables in the integer valued world. So examples. The first example I want to tell you about is the simplest one perhaps. It's called Bernoulli. And this Bernoulli will have a parameter p random variable. So RV stands for random variable. Okay, so what is Bernoulli? First of all, the parameter p is a number between 0 and 1, a real number, that's a probability. And the Bernoulli random variable just takes on 2 possible values, either 0 or 1. 0 with probability 1 minus p, and 1 with probability p. That's what one gets if, for example, if we have an event E, then the indicator of the event is a Bernoulli random variable. The indicator of an event is defined to be as 1 if E occurs and 0 if E's complement occurs. That's what the indicator of an event is. Now clearly this is of that type, and the parameter of this Bernoulli random variable is going to be the probability of the event, right? So the probability that this indicator as your random variable is 1 is of course just going to be the probability of E. So maybe I should call this random variable X. Let's call this guy X. And so the probability that X is 1 in that example is going to be P of E. And the probability 0 is 1 minus P of E. So this is going to be obviously a Bernoulli random variable with that parameter P of E. Okay. Now to calculate the expectation variance of Bernoulli is very simple. Expectation of the Bernoulli, so if X has this distribution, Bernoulli P, then expectation of X is just 1 times P plus 0 times 1 minus P, which is of course P. So the mean of the Bernoulli is P, and actually it's good to keep this in mind. In particular, if your Bernoulli random variable is the indicator of some event, then the expectation of X, or if you want the expectation of an indicator of an event, is equal to the probability of that event. So when an expectation hits an indicator, it always makes a probability out of that. Okay? And if one wants to do the variance of X, then one can do either definitions or either forms of the variance. Let's do the second moment minus square of the first moment. Now another particular feature of Bernoulli, which is quite nice, is that a Bernoulli random variable is actually always equal to its square. If X is 0, then X squared is 0. If X is 1, then X squared is 1. So in fact, E of X squared is the same as E of EX, and that's P. And E of X was P, so I have to square that under the negative, and so the variance is P minus P squared, or if you want, P1 minus P. Notice the nice symmetry of this formula. When we swap P with 1 minus P, the variance doesn't change in that case. Okay, so this is the Bernoulli random variable. This is the first and perhaps simplest integer random variable we're looking at. Okay, the second example is going to be binomial N and P. And so in binomial, first of all, N is a non-negative integer. And when N equals to 0, then things are not very interesting. So maybe I should make it strictly bigger than 0. And then P again is a probability, so it's between 0 and 1. Okay? And the scenario is that we perform N independent trials of the same type. N independent trials are performed. And X, the random variable, is going to count the number of successes. Of course, it's important to notice here that each of these trials will have the success probability P. So success probability is exactly that parameter P. Okay? And X counts the number of successes. It follows, of course, that this can be anything from 0 to n, any integer from 0 to n. And the mass function, so the probability that X is k, or P of k, is for any k between 0 and n integer, it is going to be the binomial coefficient, n choose k, times P to the k. And let me introduce yet another notation, Q. So from now on, almost always, well, maybe not at the second half of the unit, but at least for a long time, Q is always going to be 1 minus P. So that's the notation, that's the short abbreviation I use. And then the probability that x is equal to k is going to be n choose k, p to the k, q to the n minus k. So why is that? Just inverse. Everybody has seen this before. The probability of having k successes at the beginning in a row is p to the k, and then n minus k failures for the remaining trials is q to the n minus k. But this is just one way that this event can occur, x equals to k. This event can occur in other ways too, and all these other ways are the orders of successes and failures, and this exactly is counted by n choose k. So I suppose everybody is seeing that the binomial is important, but here is one more reason why it's important. The binomial random variable with those parameters np in distribution is the same as n IID Bernoulli random variables. Yet another abbreviation. IID, as usual, stands for independent and identically distributed. So if you add up Bernoulli p's, n of them independent or the same parameter, then the sum of these Bernoullis is exactly the binomial. And that's very easy to see if you imagine the n trials. So this is trial 1, trial 2, trial n, so these are the n trials. And you count the number of successes. At each trial, the number of success can be 0 or 1 because it's just one single trial. And so that each of these trials, the success number is going to be a Bernoulli itself. These are independent trials. If you add up these Bernoullis, you end up with the number of successes. And it's not very surprising then that the expectation of x is going to be the sum of the expectations of these xi's, which is n times p, expectation of the Bernoulli is p, and the variance of x is going to be the sum of the variances n times p times 1 minus p, or if you want n times p times q, q is 1 minus p. The expectation of finite number of random variables is always summable, so it's always summed up of the individual expectations. The variance is always summed up here because we have independence of the xi's. So for independent random variables, finite number of them, the variance of the sum is the sum of the variances. Okay, so these are the important things to know about binomial. So it has the mass function, it has the variance and the expectation. Now, just one remark here: why is this a mass function? So how do we know that this is a proper mass function? Well, it's clearly non-negative, but how do we know that if we sum up for all possible values from 0 to n choose k, p to the k, q to the n minus k, how do we know that this is indeed 1? Well, that's coming from Newton's binomial theorem. Newton's binomial theorem tells us that this is going to be the sum of this quantity here and the other quantity there raised to the nth power, but q is 1 minus p, so p plus q is 1, and so this is 1, so it is indeed a mass function. Okay, so that's the binomial random variable. Okay, let me move on to the next one, which is going to be Poisson. So the Poisson random variable is coming from the binomial via a limit, and we're going to deal with this later on, but probably everybody remembers that from probability 1. If we have, so Poisson lambda random variable, lambda is a positive real. If we have a binomial random variable, so I'm going to write here limit of binomial n and p, but in fact p will be a function of n. If n goes to infinity, p of n goes to 0, and n times p of n converges to this number lambda, which is positive fixed real number. Okay, if that's the case, then the limit of the binomial is going to be Poisson. We are going to prove this statement later on, and we're going to deal with this a little bit more, for now, let me just mention this fact. There is an easy way to check this directly on the level of mass functions. And so the Poisson random variable x can be any non-negative integer. There is no bound on it, so it could go all the way up. And the mass function, the probability at x equals to k, or the mass function at k, is going to be lambda to the k over k factorial and exponential to the minus lambda. And this is for every k non-negative integer. To sum this up, one just does the definition of the sum of something to the k over k factorial, which gives exponential of lambda, together with the z of minus lambda, one gets 1. The expectation of Poisson is lambda, and the variance of Poisson is also lambda. Okay, so that's not very difficult calculation. I'm not going to do it here. And again, it comes from the limit of binomials. All right, the next one I want to show you is the geometric. And it will have a parameter p. P is again a probability between 0 and 1. And so the story behind this is that we have a sequence of IID trials. It's actually an infinite sequence of IID independent trials. Each of these trials has the same success probability. So let me put here of success probability. P, and P is this parameter here. And in this infinite sequence of trials, we are going to look at the number of trials needed to see. So X is going to be the number of trials needed to see the first success. Okay, that's the geometric random variable. Clearly this is going to be any positive integer, again not bounded. And then the probability mass function, the probability at x equals to k, whenever k is at least 1, integer of course, is going to be q to the k minus 1 times p, because in order to see the first success at the kth trial, we need to have k minus 1 failures at the beginning and then a success. Now it's not very hard to first see that this is indeed a mass function. So what happens if, okay, I'm going to call this p of k as usual. Notice that this p is a mass function. This is not the same as that p as the parameter of geometric. That's just a notational thing. There is not enough letters in the alphabet. So if I'm going to do a sum from 1 through infinity of q to the k minus 1 times p, then it's just the geometric sum. There is a good reason this random variable is called the geometric, because this is the geometric series summed up. And the general formula for this sum is first term, which is q to the 0 times p, 1 minus q to the number of terms, but the number of terms is infinite, so 1 minus q to the infinity is 1 minus 0, over 1 minus q. Clearly this is only true when q is less than 1, so if p equals to 0, then there is never coming, with probability 1, there is not going to be a success, and then of course if p equals to 0, then yeah, well, okay, if p equals to 0, then this is always 0, so there is no question about it. So this formula is of course only for, actually this formula is only for p positive. Okay, now 1 minus q is p, so 1 over p times p is just 1. That's why this thing is a mass function. And then the expectation of x is 1 over p, and the variance of x is q over p square. where q is 1 minus p. And this all here is probably the way you have seen a geometric random variable. We are going to have actually two kinds of geometric random variables, and this one I'm going to call optimistic. Optimistic because it looks at the first success. And I'm also going to define the pessimistic geometric random variable, which we are going to use as well. The pessimistic random variable is, I'm going to call this y, is the number of failures. So the experiment is the same, we have independent trials. The number of failures before the first success. Okay, and clearly, if you need 10 trials to see the first success, then before that you have seen 9 failures. So this is always going to be one less, at least in the same experiment. It's one less than the optimistic version. So if x is the optimistic random variable, y is the pessimistic, it's just one less. So what is the probability for y? That it equals to k. So what is the probability that we see exactly k failures before the first success? Well, clearly here k could be 0. So let's notice first that y could be 0 actually. It starts from one less than x, which is clear because it's x minus 1. And so y could be 0. What is the probability that y is equal to k? Well, we have to see k failures and then a success. So it's q to the k times p. But k, in this formula, k is actually allowed to be 0, as opposed to the formula for optimistic. Okay, so one easily checks that it's again a mass function. In fact, that mass function is just the previous one shifted by 1. And if you want to calculate the expectation of y, all you need to do is just refer to x minus 1. So this is going to be 1 over p minus 1, or with a common denominator, 1 minus p over p, or q over p. And then the variance of y is the variance of x minus 1. But the variance is not sensitive to shifts with a constant. So it's the same as the variance of x, and the variance of x was q over p squared. And I noticed that I forgot to add x here. Okay, so much for the geometric random variable. Okay, in the next video I'm going to show you the 2 more distributions, but this is already long enough, so I'm going to stop this one here and turn to the next one.